Good morning, everyone. Today I will present my work entitled Adsorbent Materials Derived from Biogenic and Synthetic Hydroxyapatite, Synthesis, Characterization, and Adsorption of Lead, Pb superscript 2, in aqueous solutions. Lead in water represents a serious environmental and public health problem. This heavy metal is highly toxic even at low concentrations, and prolonged exposure can cause neurological, renal, and cardiovascular damage, as well as affect child development. Different methods have been used for its removal, such as chemical precipitation, ion exchange, membrane filtration, and adsorption. Among them, adsorption is one of the most efficient and low-cost alternatives, and it can employ both organic materials, such as biomass or agricultural waste, and inorganic materials, for example, zeolites, clays, and metal oxides. Among inorganic adsorbents, hydroxyapatite, a calcium phosphate with high affinity for lead, stands out for its effectiveness. In this work, we focused on obtaining hydroxyapatite from the bones of the plecostomus fish, Loricaridae, an invasive species that severely affects aquatic ecosystems in Mexico. This approach not only adds value to a biological waste, but also contributes to the circular economy and the achievement of the Sustainable Development Goals, SDGs, especially SDG 15 on ecosystem protection, SDG 12 on responsible production and consumption, and SDG 6, which aims to ensure clean water and sanitation. Methodology. First, the plecostomus bones were cleaned through a hydrothermal treatment with hydrogen peroxide and deionized water. Then, we followed 3 synthesis routes. 1. Pyrolysis in a conventional furnace at 500 degrees Celsius for 1.5 hours to obtain carbonized bone. 2. Calcination in a muffle furnace at 550 degrees Celsius and 850 degrees Celsius for 6 hours. 3. Comparison with commercial synthetic hydroxyapatite, Sigma Aldrich. Each material was characterized as follows: specific surface area and porosity by nitrogen physisorption, crystalline structure by X-ray diffraction, XRD, functional groups by infrared spectroscopy, FTAR, thermal stability by thermogravimetric analysis, TGA, surface acid and basic site concentration by titration, and point of zero charge according to the Medellin-Castillo method, 2007. Finally, Pb superscript 2 adsorption tests in water were performed using 5-hour kinetics, evaluating concentration over time and fitting the data to first and second-order kinetic models. Results. Table 1 presents the physicochemical and textural properties of biogenic hydroxyapatites from devilfish bones and synthetic hydroxyapatite. The bones were treated with hydrogen peroxide to remove organic matter and then subjected to different extraction routes. The results show that thermal treatment significantly affects the specific surface area. Deproteinized bones had an area of 109 square meters per g, which increased to 128 square meters per g after pyrolysis in a conventional furnace. In contrast, calcination in a muffle furnace at 550 degrees Celsius and 850 degrees Celsius reduced the area to 50.9 square meters per g and 2.7 square meters per g, respectively. In comparison, biogenic hydroxyapatites showed a higher specific surface area than the commercial synthetic sample, except for the material calcined at 850 degrees Celsius. These results confirm that the synthesis route directly impacts the porosity and adsorption potential of the material. 1. We also found that basic sites were predominant, with a point of zero charge between 7.15 and 10.70, which favors the adsorption of cations, such as Pb superscript 2. Figure 1 shows the characterization of biogenic and commercial synthetic hydroxyapatites by nitrogen physisorption, X-ray diffraction, XRD, infrared spectroscopy, FTAR, and thermogravimetric analysis, TGA. Figure 1a, the nitrogen adsorption, desorption isotherms are classified as type 3 according to IUPAC 1, indicating the presence of a mesoporous structure in the analyzed materials. Figure 1b, the X-ray diffraction spectra show the indexing corresponding to the crystalline hydroxyapatite phase, ICDD 00-009-0432. Calcined materials and synthetic hydroxyapatite exhibit peaks of greater intensity, reflecting a higher degree of crystallinity. In contrast, uncalcined bones display attenuated peaks due to the interference of residual organic matter. Figure 1c. The infrared spectra reveal characteristic bands of the inorganic phase, such as hydroxyl, phosphate, and carbonate groups, associated with the hydroxyapatite structure. Bands attributable to the organic phase are also observed, such as CH, C=O, and amide groups, related to collagen and proteins present in the bones. Figure 1d. The thermogravimetric curves show 3 main weight loss events. 1. Moisture loss below 200 degrees Celsius. 2. Decomposition of the organic phase between 200 degrees Celsius and 550 degrees Celsius. And 3. Loss of the inorganic phase associated with hydroxyapatite dehydroxylation above 600 degrees Celsius. Figure 2 shows the Pb superscript 2 adsorption kinetics for biogenic and synthetic hydroxyapatite. The lines represent the fit to the pseudo-second-order kinetic model. Table 2 shows the first and second-order parameters obtained from the experimental data fitting. Fitting to a pseudo-second-order kinetic model indicated a chemisorption mechanism, where lead ions substitute calcium in the hydroxyapatite structure. Regarding adsorption capacity, there were no significant differences between biogenic and commercial synthetic hydroxyapatite, with values ranging from 228 to 254 milligrams per G. However, synthesis temperature did have an effect, reducing capacity under specific conditions to 51 milligrams per G. The different synthesis routes of hydroxyapatite from plecostomus bones directly influence their textural, physicochemical, structural, vibrational, and thermal properties. Compared with commercial synthetic hydroxyapatite, no significant differences were observed in lead adsorption capacity, with values in the range of 228 to 254 mg/G. However, the synthesis temperature for biogenic hydroxyapatite showed a notable effect, with adsorption capacity reaching 51 milligrams per G under specific conditions. In conclusion, both biogenic and synthetic hydroxyapatite are efficient materials for Pb superscript 2 removal from water. Furthermore, using plecostomus bones not only supports a sustainable process aligned with the circular economy, but also provides a viable technological solution for water decontamination and the mitigation of an invasive species.